Imagine dropping a hot metal ball into cold fluid. How does its temperature change over time? The lumped capacitance model gives us the answer. When the object is small or conductive enough that its internal temperature is nearly uniform at all times, the temperature decays exponentially, from the initial temperature toward the fluid temperature. Simple, elegant, and surprisingly accurate for many real problems. The lumped capacitance model is only valid when the temperature inside the solid is nearly uniform. The Biot number tells us whether this assumption holds. The Biot number compares convection at the surface to conduction inside the solid. When Biot is much less than 0.1, internal resistance is negligible and the lumped model is valid. Think of it this way: if the solid conducts heat easily, it equilibrates internally much faster than heat leaves the surface. Small copper ball in air, perfect. Large ceramic block in water, not valid. Apply the first law of thermodynamics to the solid. The rate of energy stored equals the rate of heat leaving by convection. The energy stored in the solid equals ρ times V times Cp times dt over dt. Setting this equal to negative convection gives us our ode. Substituting theta equals T minus T infinity simplifies it further. Define theta as excess temperature over the fluid. The result is a first-order linear ode. Define tau as ρ v Cp over HAS. The final result is the lumped capacitance ode. The ode has a clean exponential solution. Theta over theta initial equals e to the negative t over tau. This is a universal curve, the same shape for any material, any geometry, any fluid. Only tau changes. At T equals tau, temperature falls to 37% of initial excess. At 3 tau, only 5% remains. At 5 tau, essentially zero. Steady state reached. The time constant tau determines the cooling rate. Large tau means slow cooling. Small tau means fast. Copper with tau of 1 second cools rapidly. Steel at 3 seconds is moderate. Ceramic at 6 seconds cools slowly. Tau depends on the mass, heat capacity, convection, and surface area. You can increase tau by increasing mass or heat capacity. Decrease tau by increasing convection or surface area. There's an elegant analogy between heat transfer and electric circuits. Thermal resistance is like electrical resistance. Thermal capacitance is like a capacitor storing charge. The time constant tau equals Rth times Cth, just like an RC circuit's tau equals Rc. This analogy lets engineers use circuit simulation tools to solve thermal problems. The lumped capacitance model appears in many engineering fields. In all these cases, knowing the time constant tells you exactly how long the process takes and when to intervene. Here are the key equations: the Biot number validity check, the time constant, the exponential solution, and the total heat transferred up to time t. Challenge: a copper sphere 12 mm in diameter is placed in a flow with H equals 35. Find the Biot number, time constant, temperature at 120 seconds, and total heat transferred. Try it.